peer review journals, and many conferences. She has received engineering from Jadavpur University, MTech in Computer Science from BIT Misra, MSc in Mathematics from IIT Kharagpur. Welcome, ma'am. I would like to call you to deliver your lecture and hand over to you.
Thank you, sir, for this very nice introduction. Am I audible?
Yes, ma'am. Audible, ma'am.
Okay, okay. So I welcome you all to listen to my whatever I need to say. The since it is offline, I can't see anyone's face. So just bear with me. I know you have finished your lunch, and so I hope I will not make you sleep. So I'll just start. Actually, I got inside the link a little beforehand, and I was listening to the earlier professor who was giving a lecture, and I saw that he was talking about model and all. So it might be a little bit overlapping. So what I'm going to talk today is about data and how it is used in artificial intelligence. Okay. So when I go into data and artificial intelligence, let's start reverse. Let's start with artificial intelligence and then go to data. And this is a universal disclaimer, not to burden up my slides. I have just given it. I have a reference. If anyone needs, I can provide it afterwards. Okay. So I don't know whether you have seen this movie or not, Artificial Intelligence. It was long back, and I just want to start with this talk about this movie. This movie is a very fascinating movie. Before artificial intelligence as such was such a hype, they came up with this movie where two childless uh, uh, individuals, a couple, childless couple, wanted to have a child. So they went, this is a sci-fi movie, as you can understand. They went to the some agency who provide them with a cyborg humanoid enabled with artificial intelligence. And the parents loved the child very much. But then they got to conceive and had their own child. When the human child appeared, the humanoid actually got less attention. So the humanoid, as he was artificially he was artificial intelligence, he got to have this essence of neglect. And then he remembered a story his mother used to tell him about a blue fairy who used to fulfill the wishes. So one night when he was alone, he was asking the blue fairy to make him a real life boy. You can start with artificial intelligence, keeping in mind that this was underlining intention of all artificial intelligence practitioners or artificial intelligence uh, people who are trying to come to make artificial intelligence happen, that they will make something real just like human. Okay. So now if you think about human, what actually is so uniquely identifiable as human, which no other thing does. Okay. So what actually we think about is that whenever we have some kind of a experience, we try to learn it, we try to gather the information, we get the knowledge, and we try to use it further. So all humankind, all kind of a expression is based on the basic bottom line, which is data. That thing we are going to talk. So then this data somehow supposed to be converted into information. And then this information will actually accumulate into knowledge, and the knowledge will generate wisdom. Okay. So most of the time data is fact which themselves actually has no very distinct unique meaning. And then we have got the understanding of that data. So if we actually put understanding on the data, we will talk about information. And then if we orderly synthesize all the information, then we'll gather the knowledge. And when we properly apply the knowledge, we are supposed to be wise, we will be getting wisdom. So in a sense, when we add context to the data, we get information. When we add meaning to the information, we get knowledge. And when we add insight to knowledge, then we get wisdom. So this is how an artificial intelligence is supposed to evolve. Taking up data, processing it to information, putting meaning onto it, and then adding a foresight into this so that it will be as wise as a human being. Though I sometimes doubt human beings are always wise. Okay. So this is a process in which artificial intelligence is supposed to be evolving. So just taking a naive example of what I am actually trying to say, I hope you can see the slides. So this is a kind of a geographical manifestation of a location. A fellow is driving. Okay. So when he's driving, he is in that corner of a block and he stops. Okay. So at that corner, he sees that he knows his path. That dotted line is his path. So he wishes to move through this path. So now at that corner, when he moves or when he bends, he sees that there is a red light. Okay. So where the red light is 15 degrees south, 30 degrees east, there is a red light, which actually does not give you much of a thing about it. But if I say that the traffic light on the left turn has turned red, then it adds the context to that data, which says at 15 degrees south, 30 degrees east, there is a red light. Okay. Now, even if with that information, a person cannot do much if he do not have the knowledge of traffic movement and all. So the traffic light on the way of the car has been turned red. That means he needs to stop. Okay. So the wisdom will be he should better slow down the car. So this is how, in a very unconscious way, we actually go on processing the data to wisdom, which we do not most of the time think we are doing. Okay. So keeping this thing in mind, let's hop into the data. Okay, so data, as per Cambridge Dictionary, is defined as facts, numbers, collections to be examined, then considerations or decision makings and all. And digital data that we are interested in when we go for actually doing any kind of a data process. Manually, we rarely do anything these days. Okay, so digital data is manifestation of such data in zeros and ones. We all know these things. Okay, so there are different types of data, qualitative and quantitative, if you actually define them. So qualitative, which actually tells about the quality of the data, whereas quantitative, which you can actually count and have kind of a mathematical operation on them. Okay. So then qualitative data, we can also again divide broadly in structured, unstructured, and semi-structured data. So structured data is the data that is created using predefined schemes or predefined formats. That means a typically organized or data in previously known or previously decided upon way of organizing them. Whereas unstructured data is just stub of data you just put in. You don't have as such any structure or predefined manner of organization. Whereas semi-supervised is a kind of a both. It's like having both parts together. So it is a form of structured data that does not obey any fixed kind of format or data model. But nonetheless, it contains tags or other marks or markers to separate different element of data so that we can understand that, okay, this is one part of the data and this is another part of the data. This bifurcation is understandable, but we don't know exactly where the first bifurcation starts and the second first bifurcation ends and the second starts. So it's a kind of a having the both but not having anything very concrete. Now, just hold on. Now, structured data can be of two types: a nominal data and an ordinal data. Nominal means nomen, that means it has name. So the nominal data is labeled or named data. So if you have a nominal data, that means you have every data point put into some name or some label. Okay, you divide the whole data set into some smaller groups with a group name tagged into them. Data does not measure or evaluate. In this case, it is just assigned to this group. So group 1 is, if you want to have a data of group 1 and group 2, you cannot add it. You cannot actually evaluate as such, but you can actually classify them, or you can actually take an account that this is different from that. The groups are unique and have actually no common elements in nominal case. The order of the data collected can't be established using nominal data. Thus, if you change the order of the data, is the significance of the data. That means you are not telling that if the data is belonging to class 1, it has a higher importance or higher class than it is belonging to class n. It does not work like that. Let's take a small example. Suppose I have 4 different groups: blue, red, green, orange. Or I have 2 different groups, female, male. Okay. So when I am just writing blue, green, red, orange, it has no order whatsoever. So this table where I am actually accumulating this data, you can see that age, color preference, and sex. Okay. So 12 age, color preference red, female, and 55 age, color preference blue, female. Okay, they actually are not in any kind of order. It's just, it is. You cannot say that 12 age comes first and 55 age comes last in this specific way of representation. Okay. Now, suppose I want to make them in order. Rather than giving them big names, I represent them in numbers. So if I number blue as 1, red as 2, green as 3, orange as 4, and female I number as 1 and male as 0, then I can again get this one. I can again convert the previous table into the next table. But still, there is no mathematical calculation that can be done even after I have changed and now named them numerically rather than having their qualitative naming. Okay. So ordinal data is a categorical data, and it's a ordered category. That means there are, now you can say, you can find out that one is nearer to something and one is far off to something. So ordinal data is distinguished from nominal data because they have a ranking. So yeah, if you say the data is ordinal in nature, you can actually say this comes after this, this comes after this. But the point is that you can actually not say how after. Okay. So let's take this example. Suppose you are marking a paper. Suppose you are reviewing a paper and you are having this kind of a scenario. You have strongly agree, agree, disagree, strongly disagree. Okay, so you know that strongly agree and agree comes one after another. Agree to disagree, then disagree to strongly disagree. But can we ever actually find out what is the difference between strongly agree and agree and disagree? Okay, I can say that if I am in the agree and then I have another one in the disagree, the difference is almost 180 degrees, huge difference. But what's the difference between disagree and strongly disagree? Where do I start uh, being strongly disagreeing with something and stop being normally disagreeing with something? Okay. These things are ordinal, but it is very this distancing is not actually one mapping with the number system. That means they are not equidistant, but they are in a certain order. That's why the data is ordinal. Now in quantitative, you have got a discrete data set. Discrete only takes certain number of values, countably finite. Whereas, oh sorry, just hold on a second. Okay. Whereas if you have taken continuous data set, is infinite. You can have a huge number of data and you cannot count them as such. Okay. So discrete is if you are throwing a dice, the number of the side that comes on the top is discrete data set. And if you are calculating someone's age, then it's a continuous measure of data set. Okay. Now, keeping these all things in mind, as you have already heard, we need to learn from this data. Only then we will be able to gather the knowledge. Okay. So learning from data is a real difficult issue while we are considering the artificial intelligence. There are so many ways we actually learn and use that data set. So as our background knowledge to take a call, that it becomes very difficult to how to say, to take out a single way of learning if we do not actually understand how the things are learned. Okay. So now we will talk about fitting a data in a model. So fitting a data in a model is in a sense learning the data, learning the situation getting from the data and representing it through some kind of a model. So it is kind of an acquisition, not only acquisition, a manifestation of knowledge. Models can be actually considered as acquisition and manifestation of knowledge in artificial intelligence. Okay. So learning have different definitions provided by different people. Okay. So some of the very well-known definitions are act of experience, knowledge or skill acquired by instruction or study, modification of behavioral tendency by experience. Okay. That means exposure to the certain conditions lets you behave in a certain way. So act of experience is various. We see, we hear, we taste, we touch, and we smell. And all these acts of experience, as we do in the human beings, are being mimicked in artificial intelligence to actually use it as a learning procedure. Okay. Then you have got instructions or study. Okay. So instructions or study is a very well-known procedure of gathering knowledge. And this is also being done in artificial intelligence. Writing the instructions to process the information to gather the knowledge. Modification of behavioral tendency by experience. This is more or less the hallmark of your artificial intelligence, because most of the artificial intelligence techniques are heuristic and they learn by experiencing the data. So they modify them. They are all self-modifying as human beings are when they are exposed towards the external stimuli or the environment as such. Okay, which is the environment in the case of artificial intelligence is the data. So how do we actually, in very naive term, talk about artificial intelligence? Do you think making machines act like human beings are magic? To me, it's more like a gardening, if you think. So the seeds will be your learning techniques, the nutrients will be your data, You are the gardener. That means the people who are using those learning techniques and using those data are the gardeners, and the plants that you are getting out could be considered as the models of the result of learning. So let's talk about the models now. Whenever we talk about the model, the first thing we need to address is what is a parameter? What are parameters? Okay. So if you think about properly, the parameter, as they say, is an arbitrary constant whose value characterize a number of a system. Any unique individual of a system is being pinpointed by a fixed value of the parameter. Okay. So let's take an example then. We are taking the two-dimensional coordinate system, and we are having the axis along with horizontal as x-axis, the axis vertically up as y-axis, and cross point is 0. Now let us consider a straight line, an equation of a straight line. We all know the equation of the straight line is y equal to mx plus c, the generalized equation from our school days. And as we know, m is the angle made by the line with the x-axis and c is the intercept. Now, when we have yet till date talked about an equation, we have always considered x and y, the variables. We put emphasis most of the time when we are using this equation about x and y. But what exactly is x and y? Are x and y? They are variables. They move. They are the points moving on the line. So if the line exists, they exist. If the line does not exist, or this another line, this x and y does not exist. But then who is going to fix up whether this line exists or not, or which line I am talking about? Okay, so suppose let's take another m, which is m1, or another c, which is c1. So is y equal to mx plus c same as y equal to m1x plus c1? Definitely not. They are two separate lines. So who decides that this line is different from the other line? M and C. The value of M and C decides whether this is this specific straight line model I am using, or the other specific straight line model we are using. So when we are going to uniquely identify a model for a special scenario, we need to identify its parameters. Without the parameters, the models don't exist. So different kind of parameters are there, of which the most important parameter while generating a model or while establishing a model is called model parameters. These are the parameters in the model that must be determined using this training set. And these are the fitting parameters. That means if I have a data set, I will try to make a model which will fit this data set. In essence, this whole procedure of fitting a data set or fitting a model into a data set or vice versa is actually fixing up this parameter, which are called model parameters. So you can see you have got a data set, need to fit a model. So when you need to fit a model, we actually need to find out M and C for this specific case, very naive straight line model. So there might be different other models with different other parameters, but the essence is that if you have got a data set, if you need to find out a model mathematically which expresses the characteristics of your data set, you need to find out the parameters. Okay. Now there are some other parameters which are said to be hyperparameters. These are adjustable parameters which must be tuned in order to obtain the best model, that is. For the example, we normally have the learning speed, number of nodes, hidden layers, number of epochs, etc., etc. These are all hyperparameters. Okay. So in essence, model design plus hyperparameter tuning actually gives you the model. That means actually it decides or fixate up the model parameters. Okay. So why hyperparameters are at all something we are talking about? Good choice of hyperparameter really makes an algorithm to be standing out. So let's take a very naive example of it. I want to move from the location A to location B. Okay, so this is the shortest distance, y equal to mx plus c, m and c is the parameter. So this is another way of moving from the location A to location B, which is having one another parameter, which I have named as theta. Now there's another road from A to B, which has parameters alpha and beta. In essence, if you just by looking at it, you will decide that shortest distance is the best distance. Okay. Now think about your hometown or your city. You are moving from one location to another location. Suddenly there's a huge rain or something has happened in your road and this road is closed. So will this still be the shortest distance, be the ideal model to be taken for the path from A to B? Or might, so let's take, by looking at this load which is topmost curve, that is theta parameter, is another very nearest one. But then as I am from Calcutta, I know what this is. I hope you people also know what this is. Someone has gherowed the road. What to do then? So even if the third road is the longest road, you will have to take the longest road. Okay. So this in between criterias that actually fix it up. This is a very naive model. Don't take it as I'm just trying to give a better perspective. Don't take it as it is. So what I'm trying to say is that there are certain factors that actually makes a specific model better model than others. And that factor is actually the hyperparameter, which should be fine-tuned to the algorithm that will be giving our best model. We want to compare different algorithms with each other and oftentimes predict which is having computationally best way of handling our data set. Okay. So then what we are actually doing is we are having a data set, we are having an algorithm, we are making a model. This is most of the time we do with your artificial intelligence, especially in machine learning. So now, as we have already got into model selection, let's talk about what is model selection. Okay, model selection is a very real life way of handling a situation. When you are standing in a crossroad, you have different paths to move on. Which road do you choose? You are having a scenario, which is your data set. You want to find out the best way to represent the data set. There are various ways to represent the data set. Which one will you choose? Which is the best one? The moment I say which is the best one, I, in the next breath, tell you that you should get over the idea of choosing anything which is best. It does not happen. Real life best does not happen. So all models, since their data have noise, different kind of sampling noises, then incompleteness, then other limitations depending on the model type, constraints. Okay. Therefore, finding the perfect model is not most of the time feasible. So instead, what we search as we go on is a good enough model. Okay. Life is not perfect, but it should be good enough. So, uh, what do we think we should do when we are choosing a model? It should be good enough model. So, now need to know what is a good enough model. A model that meets the requirement and constraints of all the stakeholders. A model that is sufficiently skillful given the time and resource available. Most of the time you do not have, at least in our country, we do not have infinite amount of resources or time to come up with something. We are in a very stringy situation most of the time. A model that is skillful as compared to any naive basic models, and a model which is skillful relative to other existing tested models, better than the other existing tested models. There can be many. A model that is skillful relative to the state of art. If you can come up with such a model, you have got a good enough model. So whenever you are trying and you are literally struggling to find out a best model for your data to work on, think don't panic about whether it is the best or not. Please search for something which is good enough. So next, we must consider whether it is sufficient or not. So model selection requires sufficient enough data. This is another one. What is data? As we have discussed already, data is the manifestation of the scenario. Okay. So if we do not have sufficient data, how are we going to find out the best way of modeling them? So sufficient data is a must, but then sufficient data in this age is, it can be varied from a few thousand terabytes to a huge amount of data. Okay, so depending on the complexity of the problem, we need to find out what is the sufficient amount of data you need to have to construct that model. Okay. Now we want to go to the other things, which is called, how do we now take this data and train and use some kind of a training procedure to actually get the model. So there are different ways of doing this. Okay. Most of the time, if we have a data set, we break the data set into different sets: training set, testing set, validation set, so that we can train and test and see how the model that I have chosen is performing on my existing data set. So there are two main class of techniques which we do. One is the probabilistic measure, choosing a model via in-sampling error and its complexity, and resampling method, choosing a model via estimated out of sample error. Okay, we will come to these things. Now you think about a data set. This is my whole data set. The data points which are represented by green are the data points which I will be using for training the data. And after the training is done, we will be using the blue data set to test whether my training procedure is well enough. Okay. So suppose then, just hold on a second. So we are trying to fit a model into this data set, which will be our training data set. This is the model that I have found. You can see that not all the points of the data set are typically on the exactly on the model. It is a heuristic model, you understand. So there will be a little bit a shift in here and there. But there is one data which is totally outside my data set. So this data is actually an erroneous data while trying to fit this data set into this model. This kind of a data which does not fit the model at the time of training, however good you train, is called the in-sample error. So this is the in-sample error. After this, I go on testing whether the data set is, now I throw off the green points and I take out the blue points and see whether the blue points are satisfying my model or not. So you can see there are 4 blue points, of which one is not satisfied. Okay, but the rest of them are satisfied. So there might exist a very few number of data points which will not satisfy the forecast or the test for the model to be proper. So those data sets which at the time of testing does not satisfy us are called the out of sample error that we discussed previously. Okay. So taking this noise in this knowledge into account, let's get into how do we fit the data into the model. Okay. So now this fitting of data into the model is a sub part of your artificial intelligence, which is most of the time says to be machine learning. We couldn't fit a model onto training data and can't say that the model will work accurately for real life data. If you have a test data set and the model is running properly, you cannot say that it will run for unknown data. You have to check a model with respect to an unknown data set to verify whether the model is learning properly or not. Now, how do I get an unknown data? Should I go and to the roads and fetch unknown data? Normally, we don't do that. What we do is we take out the data and split the data into 2 parts. The bigger part we keep for training, and the smaller part, most of the time smaller part, we keep for testing. So if I train with the bigger part, I am not including any of the smaller part data while training. The test data remains as unknown data set for the model. So now if I test with the test data, which is unknown to the model, and still the model works perfectly, then I can tell that, okay, it is being somewhat tested into unknown data set and still is giving good performance. Okay. This process of splitting off of data and testing and training, this whole method is called cross-validation technique. What is a cross-validation technique? It is a technique in which we train our model using subset of data set and then evaluate it with the complementary subset of the data set. So complementary means no common element between them. The 3 steps involved in cross-validation is, first you reserve some portion of the sample database for the testing, use the data set for training, use a little portion for internal validation, and then move on to testing so that you can actually find out whether it's working or not. There are 3 different test training models which which incorporates all kind of such splitting procedures. One is called holdout, one is called cross-validation, and the other is called bootstrap sampling. These are the most well-known methods of doing this. So what is a holdout process? You hold out some data point for further use and do not use them at the moment. Okay. So what is actually done is, if you consider these points as your data set and 2 sets as training set and testing set, you randomly select some of the data points for training and some other data point for testing. While the training procedure is going on, you take out some data points to validate whether the things are working or not. After the training process is done, you have generated a model. Now you take out the testing set. when you take out the testing set, you will be trying to see whether the test data is giving accurate result or not for the model. If the test data gives you considerably accurate result, then you can conclude that this method of training and this method of generating a model is good enough. Okay, so this is your holdout. So the basic concept of estimating a prediction using holdout is given by given a data set, partition it to two disjoint sets and call the training set, I call them training set and testing set. Classifier is learning based on the training set and gets it evaluated using the testing set. Now the point is that how many data should I keep for training set and how many data should I put for testing set? This is most of the time the discretion of the evaluator, and most of the time actually a hallmark representation of who is using it properly on, who is not. So there is a trade-off. So the point is that if we have too large of a training data, then the testing data will be small. It's kind of, you have a huge syllabus which you have taught and you have only given question from 2 modules. So you cannot, if you have lesser testing data, you cannot be testing the students in a more holistic manner. But if you have got more testing data and less training data, then it's just the vice versa. You have studied, you have taught very small syllabus and you have given questions out of syllabus. So since you have not trained the students or the model using the data, of course they will fail. So this trade-off is very delicate to fine-tune most of the time. Now we move on to a upgradation of the holdout, which is said K cross validation. K-fold cross validation is one more improvement, as rather than having 2 sets of data, the whole data set is divided into K smaller subsets of data. So when they are doing the training system, it takes out 1 subset as test set and the remaining K minus 1 subset are used as training sets. So, and what happens is that the average error across the K different trials are computed. Now, what is then the advantage? Why we are going on doing it over and over again? The advantage of this method is it's not very important how you divide the data, because throughout the whole procedure, at least once every data gets to be acting as a test data, and throughout the process, every data gets to be acted as a training data for K minus 1 times. So let's just see what actually is happening. Suppose this is my data set and I have divided the whole data set into K different groups. Okay, so now I am using any learning experience to generate a classifier or a model. So what happens is that, say first time I'm taking F2 as a test set and F1, F3 until Fk, all these K minus 1 sets as the training model for the learner. Next time I'm taking F1 as the testing set and F2 to Fk, all the other K minus 1 data set as the training set for the learner. So in this way, you can see that every group gets 1 time to test the learning procedure, whereas every group gets K minus 1 time to participate in the training procedure. So it is more holistic, their training, because no data left which is actually included in the data set but has not gone through the training procedure K minus 1 times, as well as every data set has been tested. But then what is the disadvantage of this method? The problem with this method is every time you train and test, every time you change the folds, you have to do the whole thing from the scratch. So there's a huge computational complexity which is there. Now, a variant of this method of having this kind of a scenario done is called random sampling. So you take randomly, you take out the different data and you go on testing and go on training. You do not have to do this whole thing k times. Suppose this is a data set and you can see that we have got two different ways of breaking the data set. So every time we do it, every time we break it up, it takes out random numbers and repeats it. Till when it repeats it? Till the time I find or the model is giving you a steady result. Till the time my prediction is accurate, whatever data I take as a trading testing set. Sorry. So that is your random sampling. With that, we will move on to the last kind of a sampling that we'll talk today, which is called bootstrap sampling. I don't know whether you have heard this name bootstrap or not, but bootstrap actually in computer science and any other field is the phrase means that one should pull oneself up by its own bootstrap. What was that all about? Before we had our fair share of James Bond and other superheroes, Germany used to have one very unique spy whose name was Baron Munchausen. So there was a series of stories where this fellow was spying around. So one of such stories said that this Baron was moving on his horse and he fell into a deep lake. The horse ran off, he was stuck in the mud. And it was winter night and it was snowing, so what to do? So he thought that he will die over there stuck. Suddenly he got a metaphorically to say bulb lit up in his head, and what he thought is that why can't I pull up myself? And he got hold of his boots and pulled the boots so hard that he jumped out of the lake, and thus he contributed to the system of things which are called bootstrapping. So in this bootstrap sampling also, we impose the pulling things themselves. Bootstrap method is a variation of repeated version of random sampling. So the sampling of the training records with replacement. So every time someone turns up, some data is taken out, it is again replaced for the next turn of sampling. Each time we select a training set, it puts back to the original field so that it can be used. So bootstrap is a strategy which adds more randomness to the situation. So it is more useful to handle very uncertain conditions. As well as bootstrapping does weird to the distribution of the data set, which is not very much which is not very explicitly examined for a long time. So let's see what bootstrap is happening. You can see that the first data set is going like this, the second data set is going like this, and the resultant data sets are all going like this. But now you can see that the samples are not unique in nature. They have repetitions. So which sample occurs in which training procedure is not known. They can occur in any combination. It's not unique way of occurring. So the same data set can occur n number of times, or same data can occur n number of times for the learning procedure. Okay. So it gives onto the, it attributes onto the randomness and more generalized way of understanding the data. Now, after doing this, let's talk about the framework of interpretability of a model. Okay. So if you think about the framework of interpretability of a model, there are different ways we can actually frame a model. Depending on the complexity of the learning, we can have a linear monotonic model, we can have non-linear monotonic model, non-linear non-monotonic model, different kind of models we can have. Depending on the scope of interpretability, we can have a local model onto a smaller amount of data, or we can take the whole environment and come up with a global model. Now, depending on enhancing trust and understanding, why we needed this thing is that whenever we talk about artificial intelligence and all, human beings are not very trusting. If they don't know what's happening, whether it's happening or not, it's difficult for us to trust onto anything. So the mechanism that results to an interpretable model, that means you can interpret what's happening, which is transparent and dependable model, then we will be having more faith onto the model. So if I can understand a model, if it is transparent about every transaction it's happening inside, then we can trust the model, and then we can actually say it is a fair and accountable model. So black box models are little difficult for us to understand as well as trust much, because we don't know how the things are changing inside. So we as a human being, when try to import an artificial intelligence, we need to have such models which are understandable and transparent. Otherwise, we'll always see that we will always worry that the machine will conquer and put us as slaves. Okay. Then application model. A more application area of the model is also very specific, very diverse in nature. Models can be agnostic about the scenario. That means model can be generic models applicable to everything. Models can be specific in their domain, domain specific, domain agnostic. So we have models, we can come up with a model which work in everything, or we can come up with a model which is specialized for a specific sector or specific data set or a specific application. Okay. So these are the frameworks in which we actually find out how the models can be interpreted. Now, we'll talk about a data in the model, and when we are fitting the data in the model, we need to think about how good the fit is. So whenever we talk about goodness of fit, we come to talk about another childhood story, the Goldilocks and the Three Bears story. If you remember that there was a story of three bears, who stayed in the jungle, and the bears started making porridge one morning. The porridge was initially too hot, so they went for a walk. And then there was a girl who was roaming around alone, came to their house and thought, and as he was walking as a small child, he felt very hungry, so he wanted to eat something. He found at that home 3 bowls of porridge. One was too hot, one was too cold, and one was of just right temperature. So the child Goldilocks took the just right bowl. So this just right or perfect, or rather just perfect fitting of your criteria should be there in a model. So all the statistical models have different kind of fitting that are there. A statistical model is said to be underfit when it cannot capture the underlying trends of the data, when we cannot understand, when it cannot represent the data itself, when its characteristic of the data set, the knowledge of the data set is not properly manifested. A statistical model is said to be overfit when we are training it with a lot of data, and all this data also have some noise and inaccuracies in it, and we also incorporate those things. So overfitting is when we have fitted every data of to the model and included fitting the wrong, inaccurate, noisy data into the model. So though it is overfitted, it is not the perfect one. And then in between is the Goldilocks zone, where it is neither underfitted nor overfitted. As Goldilocks said, it is just right. Okay. So how do we talk about which is just right? To understand the situation which is just right, we need to talk about some other criteria, one of which is bias. Bias is very frowned upon in our normal vocabulary, but when we are talking about bias in a model creation, it is an essential part of a model creation. Why? Because bias are simplifying assumptions that make a model bias is a simplification of the assumptions made by a model to make a target function. That means bias is our background, a prior knowledge, the knowledge with which we have got into the system, okay, or the knowledge with which we have come to encounter the system. So prior to getting this database, we also had some knowledge which was there before we have encountered a situation. Bias is that knowledge. So bias is actually our start point. So low bias means suggests less assumptions about the target function, whereas high bias means it has got more assumptions, more suggestions about the assumptions. Okay, so let's say about an example of bias. Suppose we are talking about salt intake and blood pressure. So this is what is our bias, what we think, that as I increase my salt intake, my blood sugar is supposed to increase. This is my start point. This is what we have known. So this is the curve. Then we get the data set and we fine tune our basic initial knowledge according to the data set, because depending on other criterias, blood pressure can increase and decrease depending on how you are. If it is genetic in nature, you have medications for blood pressure to reduce it, to increase it. You have certain stress conditions that you are going on. Not always blood pressure rises because of the salt intake. Okay, so now this data set gives us that knowledge that, okay, this is how things have happened. So let's fine tune our model from that x equal to y straight line to this curved line. Okay. So bias actually is the knowledge that humans or that the people who are training the set comes with. Okay. So I'll just tell you one another example of bias. If you have heard of it or not, I don't know. This Amazon was going through a recruitment process which ended up being biased against women, because the criteria that was set in 1960s for Amazon has not evolved. That was their background knowledge. So whenever they are using artificial intelligence to suggest a CV or a biodata of a candidate, those older knowledges were taken into account, and hence there was a bias going on. So the bias is actually prior knowledge, but also it is the start point. So what is a variance? Variance is, we all know the statistical variance, but in artificial intelligence, variance is the amount that estimated of the target function is away from the actual training data. So If it's a low variance, we can have small change into the estimate of the target function with the data set. If it's a high variance, the data set, existing data set, and my estimation is very far off. So let's see how it works. In the same case, this is our estimation function. So what is the bias? My thought process is the bias, and the change from the actual bias to the original model, the difference between the data set, every data point from our thought process is my variance in the data set. So now, taking into this bias and variance into account, let's think about what is a good fit of a data. Okay, so this is an underfit data. As you can see, every data element is outside. This is more or less a best fit of a data. And this is an overfit of a data, because you can see that there are some points which are very far off from the model. Okay. So you can have an underfit model, which is a bias model. You can have an overfit model, which is a variance model, or you can have a trade-off model, which is the perfect fit model. Okay, so high bias, underfit model, high variance, overfit model, whereas the trade-off between them are the accurate or the more or less good enough model. Now, then we need to actually reach to this bias variance trade-off to get the better model. Okay. The problem is that there are different ways of giving the model. Model can be the learning procedure of a model can be linear in nature, which is often having high bias but low variance. It can be non-linear in nature, which have low bias but high variance. So how do we actually come up with a part where we increase the bias, it will decrease the variance, and if we increase the variance, it will decrease the bias. It's kind of a reciprocal kind of a scenario. So what we can do is we take the model complexity and we take the prediction error and we plot the bias in this infrastructure or in this coordinate set. And then we plot the variance also. Now the optimal model will be, you can see that the bias and the variance has a crossover at the middle. So if we take the left hand side for the bias and the right hand side for the variance, at the crossover point, we get the optimal model. This is how we might be obtaining our optimal model. So in the left hand side, it is underfitted. In the right hand side, it is overfitted. And in the middle, it is optimal solution portion. The real world is made up of different objects, living, non-living. Facts, attributes are there about them as a data. You can have different ways of expressing data. In biomedical, you have different kind of data. It can be image data, signal data, text data, various kind of data. Any attribute could be a feature as long as it is useful to the model. The purpose of a feature, other than being an attribute, would be much easier to understand in the context of a specific problem. Otherwise, the purpose of the features are not very well established. A feature is a characteristic that might help in solving a specific issue that we are trying to handle with artificial intelligence. Okay. So the initial set of raw features can be redundant and too large to manage. There is a word that says that the huge database is an overhead. We do not need too many redundant data. Therefore, a preliminary step in many applications consists of selecting a subset of features or constructing a new reduced set of features to facilitate learning to evolve or to generate a more useful model, which has a better generalization and interpretability. This requires the examination of multiple possibilities and combine all such automated techniques like artificial intelligence and all their subdomains and the intuition and the domain knowledge of the expert at the domain. So whatever data you get, if it is a highly specialized data, you need to have an expert who will be telling you what is this data all about. The knowledge is not all the time easier to accumulate without that bias or experience as such we say. Okay, so especially in case of biosignals, there are so many different ways the biosignals can be obtained and saved and used for various uses. But if we do not know, if we cannot extract the knowledge and use it wisely, no system, even if we have huge amount of data and highly sophisticated AI algorithms, will work properly. So this is all about data and AI.
Any questions, participants? You may ask to ma'am.
I hope I was audible throughout.
Okay.
Ma'am, I have one question.
Yes, yes.
I mean, regression case, the bias and errors are the same or it's different?
In regression case, bias and error every time is different.
So, ma'am, the intercept is the bias or
which intercept?
For example, in regression case, there is an intercept.
Line regression or
simple linear or multiple linear, any?
Linear regression.
Yes, ma'am.
Okay. So what you are asking?
I'm asking, ma'am, the bias and the error are the same terms or it's a different?
No, bias is the term that you have established before you started making the model. That means before you have started establishing the linear model, whatever knowledge you have got is the bias. Error is after establishment of the model, how much you have got the model as per to the data. So linear regression, if you think about a supervised learning technique, you will be having the data as well as the output. So your model handling the data, giving their output and original output, whatever the difference is, that's your error. Before getting into, while you are fine-tuning your hyperparameter, when you are actually establishing the learning process and all, that time you are using the bias.
So, ma'am, can we quantify the bias?
There are various formulas by which you can quantify the bias. If you read any statistical book and all, you will be getting there are various ways of quantifying the bias. But in artificial intelligence, the knowledge itself can be having this bias itself while we are fine-tuning the hyperparameters. That means the domain expert will come up with a bias.
And
so yes?
Maybe it's during the training time we are bringing bias to the model.
No. You are entering the training phase with the bias. You are not biased. The data that has been provided with you has a bias.
Second question is, what is the use of hyperparameter? Can you connect with in sample error and underfitting case?
Okay, hyperparameters are the parameters which actually tells you how well you are doing what is the best learning procedure. That means how fast the learning. If you have 4 different learning things, suppose you are using 4 different learning techniques. Okay, so you need to find out how fast each learning technique is working, how many number of nodes they will take, what are the number of intervals they will be taking. These are the hyperparameters. Hyperparameters are more wonderfully explained if you go for gradient descent. If you remember gradient descent, over there you'll be getting hyperparameter tuning more better. So hyperparameter tuning is itself a whole kind of a whole kind of a lecture that we can handle later. But if you want to understand, hyperparameters are established and fine-tuned before you get into the model. And what else you asked? Could you
I'm talking about can you connect hyperparameter with underfitting? I mean, underfitted model. Means
No, you cannot connect hyperparameter with the underfitted curve. You can connect the bias with the underfitted curve.
I mean, my question was, can we reduce underfitting kind of a thing through hyperparameter tuning?
Yes, of course.
was my
That's the training procedure. You enter with the underfitted curve and you go on training. But how fast the training procedure will be working depends on the hyperparameter. You understand? I just give you an example. Okay, you are starting with some basic things to process the data. Okay, and you are establishing a model. You are having different utensils to establish that model. Which utensils will be better is your hyperparameter, and the recipe that is you have in your mind is your bias or underfitted model. Now you get inside that using those hyperparameters, you get inside the model, you start fine-tuning the underfitted model, and you get the perfect fit. And if you go on fitting more, you get an overfit model.
Ma'am, can it also reduce the test accuracy at some time if we over-tune the model?
Yes, you will be incorporating noise. So the more you overfit the model, more you're taking the noise values, and the accuracy will go down. The more it is overfitted, the accuracy goes down. The more it is underfitted, the accuracy goes down. So the perfectly fitted model has the highest amount of accuracy. So accuracy of the model is maximum when it is perfectly fit.
And the last question, I'm just asking the last question. So how, I mean, the interpretability and explainability is the same thing or it's a different thing? The
Interpretability and
explainability.
Interpretability and explainability are not same. Interpretability means how you can interpret the data. Explainability is how you can quantify or qualify the data.
So if a model is interpretable means, is it also explainable?
Not always.
I mean, the regression case, we get some weights. So they are also interpretable and we can explain through that.
Yes, they are interpretable, but they are interpretable as well as explainable, but not all the time this can happen.
Okay,
there are exceptions.
Okay, I got it. Thank you so much, ma'am, for your answers.
Okay. Anyone else?
So thank you so much, ma'am, for taking the time to impart your wisdom to us. Your presentation on data and artificial intelligence was incredibly informative. Discussing the word DIKW stands for Data, Information, Knowledge, and Wisdom, which refers to many levels of data processing. Using flowchart or detailed explanation of what data is and the many forms of data is provided with classical examples, how AI is more like gardening, like seeding, which is learning techniques, why parameters are important, what parameters are, how to choose a model based on real-world event, and what matters. Talk about the cross-validation process at its stage, how holdout is used to estimate predicted, and discuss the food-state sampling with a story that is put yourself up. What is model farming? How does it work? And what is its application? Use graphs to illustrate the ideas of underfitting, overfitting, variance, and bias in data, and many more things you have discussed. I would like to thank you once again, ma'am, for your contribution to this STC. Thank you, ma'am.
Thank you, sir.